So this lecture is aimed at providing deep understanding on the fundamental concepts in medical or public health research. And at the end of the day, we should appreciate the role of biostatistics in health research and find a way to link statistical association to causation and what that means in its whole description. So the first thing we have to do with here now is to find out exactly what is research. When we talk about research, what are we talking about? What do we really mean? So research is an organized and systematic way of finding answers to questions. So the bold words are actually the real deal when we talk about research. It should be an organized, systematic way of finding answers to questions. So there can't be a research without a research question. So what drives research efforts is research questions. And there is need for us to know how to generate research question and also how to ask the right questions so that our research effort can be directed and focused. So that is research. And that also plays deep into the concept of study in the definition of epidemiology. Epidemiology is a field, it's the basic science of public health, and it's essentially the study of something. And because of the term study, that invites research into epidemiology. So epidemiology is essentially a research exercise that looks out for ways to explain or understand concepts wrapped in a research question. So epidemiology is defined as the study of the distribution and determinant of health-related states or events in a specified population. And not just that, how these studies, findings from these studies are applied in the control and prevention of diseases. So epidemiology is essentially a research effort. That's the key thing here, is the study, and that is where research marries with epidemiology. Okay, the next thing is for us to really have a fundamental grasp of why we carry out research. So what is the fundamental assumption in research? The fundamental assumption is simple, is that human diseases do not occur at random in a population. Human diseases have a pattern as they occur, and that this pattern can actually be described, and then the variabilities that modulate this pattern can be explained in a given population. This is the fundamental assumptions that drives us to carry out research, to find out that pattern, to describe that pattern, and also to see how we can explain that pattern, because an understanding of that pattern and the variation or variability or what controls how the pattern presents or fluctuates will help us to solve problems, will help us to predict the pattern more specifically, and also to gain control of the activities. And in this case, we are talking about either diseases or health-related states or events. So this is the fundamental assumption in research, that human diseases do not occur at random in population. So now let's come to the realm of statistics. See, statistics can be defined really in two ways. The first way is to look at statistics as a field of inquiry, as a field of study, as an arm of mathematics. And when you define statistics in that context, we're talking about the singular definition of statistics. But we can also define statistics as a word used to describe, or as values used to describe the data that we get from a sample. So that's another way we can also define statistics. So if you look at statistics as a field of study, it's the science and the art of collecting, organizing, summarizing, analyzing, and making inferences from data. So that is statistics as a field of study. So it's a very detailed field. Statistics actually is both a science that deals with theories and principles of knowledge, and also practice, the application, and art. So it's both science and art. Okay, so statistics can be termed as the universal language of science, because all science endeavors, whether formal science, physical or life sciences, has statistics at its core in explaining or dealing with data. We'll talk more about that later. So statistics can also refer, like I said earlier, as a numerical quantification of data from sample. You know, anytime you mention the word sample and you collect data from sample, then you can evoke statistics. Indeed, there is no statistics without data. Data is actually what statistics feeds on. So if there's any activity of human endeavor that generates data, then you can actually evoke statistics. And if that data is a subset of a population, which we refer to as a sample, then you are dealing with statistics. The summary of that data is actually a statistic. For example, we can have a group of a data set from a sample, let's say age of a given sample of young people, and then we look for the mean age. Now that mean age is actually a statistic because it's a single quantity that is describing a sample. That is statistics. So statistics is for sample. It describes a sample. So that is the second way we can actually define statistics, which is referred to as the plural definition. Now, statistics can either be mathematical statistics or applied statistics. Okay, mathematical statistics is that beautiful branch of statistics that deals with the proofs, the theories, the mathematical underpinnings of all the different logic and expressions that we see and use in statistics. So simple basic formula for the mean has a mathematical backbone. So the people that help us to do that, they are called mathematical statisticians. And most of the earlier practitioners of statistics, our forefathers of statistics, they are all mathematical statisticians. People like Eimer, Ronald Fisher, Carl Pearson, these guys are more mathematical statisticians, even though they also do a bit of applied statistics. But they are the ones that give us the proofs, the demonstration of the mathematical agreement between these variables and expressions that we use today. So that is mathematical statistics. It deals with the theories and the methods and all that. But when we apply these theories in a given area, in a given field of human endeavor, then we are talking about applied statistics. Okay, so which means statistics applied to any area at all is applied statistics. So when you apply statistics in the realm of medicine, biology, and public health, then we are talking about biostatistics. So biostatistics deals with data that are generated from medical practice or from biology or from public health. Okay, so that is biostatistics. That's an applied area. We are applying statistical concepts and principles in analyzing and making inferences from data in that field. Okay, now if we now look at just medical aspect, data from medicine, then we can also refer to it as medical statistics. So medical statistics can be taken as a subset of biostatistics. Like I said, there are other areas of application. If you apply statistics in economics, then we are talking about econometrics, or in our Greek, talking about agronometrics. So these are different areas, but there's something that is common to all the applied area, which is the methods and the approach that we use. Statistics is the same, no matter the applied area, the methods are the same. And we're going to talk about those methods and the approaches in next two slides. But before then, I think at this point, what is really the role of statistics in medical research? Why are we interested? Two things, two ways. One is that it helps us to improve our clinical practice because it gives us the tool we need to read published articles, bring out the findings, interpret the findings within the context of the study methodology, and then apply that in our clinical practice, which is somehow referred to as evidence-based medicine. Even though evidence-based medicine is broader than that in scope, but that is one of the concepts in evidence-based medicine. So when you have a good understanding of statistics, it helps you to appreciate published papers, and that can help you improve your clinical practice. But there's another arm, which is research. That's the second role. So statistics help us to carry out research as medical researchers or clinicians or public health experts. It helps us to do that. It helps us in every aspect of the research effort, as detailed by Douglas Hartman. He listed all these beautiful steps in the research process, starting from planning and conceptualizing of the research question. You know, you need statistical thinking to be able to come up with the appropriate research questions, and also to think about and put in focus the research problem. You need statistics. You need statistics in designing the method to answer that question, okay? In the execution, in data processing and analysis, and even in presentation of your findings to your peers and the research community, and even the ordinary non-informed scientific minds. So your ability to present data to them is key, is anchored on the fact that you understand the concept of statistics in medical research. And finally, it can also help you in publication, knowing how to publish, what to publish, and when to publish. Every aspect of publication is also part of the role that statistics play in medical research. So now let's go back to the methods and the approach of biostatistics. Now, like I said before, the approach and method is the same, irrespective of the applied area. And these methods are two: descriptive and inferential. Okay, the descriptive arm deals with how we describe the data that we generate from a research effort. It can be from a sample or from the whole population. But how do you describe? How do you summarize them? That is descriptive statistics. And depending on the type of data, whether categorical or numerical, there are different approaches that we can use, as stated here. In categorical arm, when you have a categorical data, you describe them using measures of frequency or measures of occurrence, where prevalence and incidence measures falls in. And then you can move a step ahead to also measure association if you are now looking for the association between an exposure and an outcome. Now that is in the realm of descriptive statistics, helps to describe it. Then if it's a numerical data, then you can bring in the measures of location, like the measures of central tendency, the mean median mode, the measures of partitions, like the interquartile range, deciles, tertiles, and so on. We also have measures of dispersion that help us to have an idea of the variability in our data sets. And then the measures of shape that tells us how the data sets are shaped with respect to the normal distribution. That's a term that in the course of the series of lectures we are going to upload and present, we'll discuss normal distribution and all these concepts. Now, descriptive statistics also gives us an idea on how to present data graphically. In fact, graphical presentation in terms of showing the distribution of a data set is about the first thing we should all do when we have a data set before us. And statistics, descriptive statistics comes in handy to tell us the right charts, the right graphs, the right figures to use in describing a given data set based on the inherent structure of the data sets. So that is descriptive statistics. On the other hand, we also have inferential statistics. Inferential statistics feeds on descriptive statistics. It takes descriptive statistics outcome and see how it can relate it back to the population that gave rise to the sample that we measure the data from. Okay, so it's inferential statistics help us to relay back to help us conclude on the source population or the target population that gave rise to the sample that now generated the data. And there are two methods too in inferential statistics. We talk about the test of hypothesis, where essentially we are interested in quantifying the role of chance in our estimates or in our measurements, in our data sets, and so on. Or we talk about the estimation method, where we want to now build a kind of a confidence limits, a confidence interval around our estimate that will give us an idea of the actual value of our estimate in the source population that gave rise to this sample. This may be a little bit difficult for us to comprehend right now, but as we move on in the lecture series, we'll look deep into each of these aspects of either descriptive or inferential statistics, okay? Now, this particular diagram is very key in understanding the role of biostatistics in research as a whole. And I termed it the big idea. So what is the big idea? Now, let's assume that there's a researcher who observes a given problem in the environment, in the community, or probably in a clinical practice. And this researcher is really key in finding answers to this observed problem. So it generates a research question. Now, this research question is usually generated for the population. So it is the population that will come up with a research question. We look at a given problem, we observe it, we see if we can create a pattern, and then we come up with a research question that we now want to use some research methods to answer. Okay, but there's a problem. And what is the problem? We cannot most times gain access to all the population, all the individuals in the population. We always, because of money or time, we don't have access to all of them. So what do? It's a simple logic to find a way to pick a subset of this population. And picking a subset of the population is simply taking a sample, a small chunk. That sample, usually we want it to be representative of this population. And why? So that this, whatever we get from the sample, we can infer it back to the population because the sample represents the population. Okay? So how do we pick that sample? We use a random procedure, a process called sampling. So we use a random procedure to pick a sample. And why are we using a random procedure to get a random sample? The reason is simple, because we don't want our choices to determine who we select into our sample. So we allow a random procedure to help us do that. So that process is called sampling. So we get a subset, a sample of this population. Now, it's upon this sample that we measure what we are interested in, the research question. Whatever variable we need to measure to answer our research question, we measure it in this particular sample. So let's assume that we are concerned, want to find out what is the mean age of the population where we live, or our community, and we pick a sample of 50 individuals into this particular sample. And then we measure the variable, which is age, and we get all their data with respect to their ages, and then we summarize them, we describe that sample using descriptive statistics. Because now we've gotten the data, so we describe that data, and when we describe that data, we have the mean age. Let's assume the mean age of my community based on this sample is 20 years old, 20 years. So now from the sample, I now have the mean age of 20, but there is an added question. Is this 20 years really representing my community? Are these 50 people representing my community? Did I by chance alone pick the older people or the younger people in my community? That question needs to be resolved before we can actually fully say that my community mean age, the mean age of my community is 20 years. So this sample here, what is helping me to do is try to be like a means to an end, a proxy for my population. So whatever I get from my sample, I need to infer it back to my source population. Okay, and for me to do that, I have to be able to find out that, look, my sample really represents my population, that my sample is not due to chance, Remember, I allowed chance to also help me pick my sample. I want to be sure that this is not a chance game, that this is real. So for me to do that, I need to evoke inferential statistics, and I need to evoke test of hypothesis. Test of hypothesis will help me to quantify chance. The chance that I actually picked the right sample that represents my source population. Therefore, the mean age I got from this sample represents the mean age of my population. That is great. So that is what test hypothesis is supposed to do. And for us to measure chance, you remember the very popular, beautiful probability. This is where it comes in. Probability helps us to quantify the degree of chance in an event. So here now, we have the fathers of statistics have called that p-value, probability value. Okay, so what's the probability that whatever I select, the number I selected, these people there actually represents the population. The probability that that chance is what selected them. If it's too high, probability of chance being responsible, if it's too high, then I cannot really conclude that whatever I got from my sample represent my population. It could just be due to chance. But if the chance is very small, it's very low, I can say, well, this sample, could represent my source population. Therefore, the value I got from my sample is representing the value or the parameter of my population, which means the mean age could be 20 years in my population. Okay, so that is test of hypothesis. On the other hand, there's a different way we can think about it. The same problem, but in a different way. We think about solving it differently, which is using the estimation method. In this case, instead of looking at quantifying really the role of chance using a p-value, we want to do that same thing using a confidence limit. So since we already have 20 as the mean age of our sample, we want to build a confidence. How sure are we? What is the confidence that we are putting on it that this 20 really represents the population? And based on that confidence we are putting on it, we can actually calculate a confidence interval. And that confidence interval usually is around the estimate we got from the sample. So if it is 20, we may have the confidence interval of between 20 of 15 to 25. 15 to 25 is around 20. We construct it around it. And it depending on the confidence limits that we want to put on it to determine the size of the confidence interval. So what does that confidence interval really do? In a basic term, in a basic form, it helps us to look back at the population and say, look, the actual value of the age, of the mean age, of the estimate we are making could be between these limits. That's what it helps us to do. So if we are saying that the sample gave us 20 years as the mean age, and we have a 95% confidence that the confidence interval is between 15 and 25, it means that if we go back to this population, okay, the true population mean age could be between 15 and 25 years. I mean, that is fantastic. That is so logical. And that helps us to conclude on our population as to what the mean population age is of my community. Okay, so we can either use the test of hypothesis approach or the estimation interval approach. Either way, both tries to quantify chance and both tries to give us an estimate of what the true population parameter should be using the value statistics or the value estimate. However, estimation method of inferential statistics has other beautiful properties and other beautiful usefulness and use. For instance, it can help us to quantify precision. It can also help us do that. And in clinical medicine, it can help us to really look at what we call clinical significance. So those are terms I will look at later, not in this lecture in particular, but that is what estimation method does for us. And that is the edge, the advantage it has over test of hypothesis in making conclusion on the population from a sample. So this is the general concept of how statistics play different roles in helping us find answers to a research question. Now, lastly, let's look statistics without a causal model could be said to be dead, really, because no matter how much you observed from your study, there is need for you to make sure what you have observed is a valid observation. Okay, and when we say valid observation, it means that what we found actually measures with what the problem is, the research question. We actually measured it, okay, and that this is what it is. So for us to be able to really say that whatever we have observed from our study is a valid observation, we need to take care of these things here. They are called alternative explanation to observed outcomes from studies. Alternative explanation, other explanations that could explain what we are seeing from our study. The first one is chance, or the role of random error. And I've said it earlier, we use the test of hypothesis to quantify that, and then we know how much it is, and then we can interpret that. The second is bias. Bias is called a non-random error. These are errors that are not brought in by the inherent differences in your sample, in the people that make up your sample. It is error you bring in because of the methodology, the approach, or the thinking that you have brought into your research. So it is the researcher generated errors, okay? And that's why we refer to them as systematic error, non-random error, or bias. So bias can be from two main basic sources. Selection bias, how you picked your sample from the population, if you are doing a pure descriptive study, or if the both arms of a comparative study, you have sample that have two groups, group A, group B. Is group A comparable to group B? If they are not comparable, you can also bring in selection bias. So selection bias is not representativeness. You are not representing your population, or the two arms of your study, they are not comparable. That's selection bias, and that is a big deal. That can bring in a lot of systematic error in your study. And the other arm of bias is information bias. You have selected the sample, you have gotten the groups. Now, how well did you measure the information in terms of how well did you measure and characterize or classify the exposure, and how well do you measure or characterize the outcome? You know, so if you don't do the measurement or the classification properly, you can bring in information bias into your studies. So your methodology is key in avoiding systematic error or bias. There are other types of biases, huge amounts. On daily basis, researchers come up with biases, but these two are the key types of biases that form the basic level of bias for any form of study. Then we also talk about confounding, which is like a third variable in your research, a third variable that distorts the true association between an exposure and an outcome. It distorts. So we're always interested in making sure we control so that it doesn't distort, because it can distort the association upwards, downwards, or simply just neutralize it. So we don't want confounding to distort our association. So we can either take care of them in the planning stage of our study, or we take care of them after the study has been carried out and the data analysis. So confounding has three criteria that they must meet, that has to be present for you to declare a third variable a confounder. Now, those three criteria, we'll look at them in another lecture series. But confounding is one of those things that could be an alternative explanation to what we have observed from our study, and not necessarily the association between the exposure and the outcome. A very good example is the association between smoking and lung cancer. You know, we can observe that there is an association, a very strong one indeed, but could this be due to the age of your study participant or their sex? So age and sex is another third variable. They are both third variables that can distort the association between smoking and lung cancer. So if you're able to prove by looking at the criteria, the three criteria for confounding, that age and sex meets those criteria, then age and sex could be a confounding variable. So confounding distort associations, and we must be interested in them. when we are designing or conceptualizing our study. Reverse causality is another one. And this deals with temporality, which came first. Is it the exposure or the outcome? The natural logic is that the exposure has to be present, and then the study participant being exposed to the exposure will lead to the outcome. That is a natural logic. But sometimes it may be the reverse. It may be that the outcome of our study is actually present first, and that is what is leading to the exposure. So you must be able to tease this out. You must tease it out clearly in your study, especially starting from when you conceive your study to the analysis and even the publication or reporting your findings. It is very key. A good example is the relationship between obesity and arthritis. Which came first? So in a cross-sectional study, you may not be able to discern which came first. Is it that because the study participant became obese, it put pressure on their joints and they now have arthritis, which is the outcome of the study? Or is it that they already had arthritis and therefore they couldn't move, they have a sedentary lifestyle, and then they became obese? So which came first, the hen or the chicken? That's reverse causality. Those are things that you really have to think about when you want to explain the results from your finding. Now, if we are able to explain away all this, then and only then can we say our findings are valid. That these are valid association and that we have achieved what we refer to as internal validity. Then after that, we can now move on to the next arm of the road to causality. So we can now infer causation. I must say here that, look, causality or causation is not determined really by statistics. Statistics give us association, statistical association, but we infer causality from statistical association, we infer it. So it is inferred from the association, okay? And there are so many criteria we use. One of them, very popular, is the Bradford-Hill criteria, a set of 9 principles that we look at when we want to come up with a causal argument. Could this association that we have observed in our study be causal? Remember, before we talk about this at all, we should have a valid association. We must have taken care of these gentlemen here, which is the alternative explanations. So by the time we have a valid association, then we can say, can we infer causation from the valid association? And Bradford-Hill criteria, one of the ways we do that. There are other ways that are other principles that we can look at when we are dealing with causality. So statistical association needs causal models or criteria for us to infer causality. So I want to say thank you everyone for being part of today's lecture series. I hope it's very informative. Statistics in medical research, statistics is very key. Anywhere there is data generated, then we evoke statistics, and statistics also help us to plan research, to carry out the research, to analyze, to interpret, and even to publish. Statistics is very, very key. And just to end with, it is said that statistics is the language of the sciences. So I want to say thank you guys once again for being part of this lecture series. If you have any questions, please don't hesitate to drop it in the comment platform, and I will find and I'll provide answers. And please don't forget also to subscribe and like, and give us a thumbs up if you like what we are doing, and also subscribe so that by the time we come up with newer videos, you will be the first to know. And always remember that science and statistics is the backbone of critical thinking process.